In the outer reaches of the solar system, beyond the orbit of Jupiter, beyond the warmth of the sun's embrace, there exists a world that defies every assumption humanity once held about the cold and the dead. It drifts in perpetual twilight, a moon no larger than the length of the United States, caught in the gravitational theater of Saturn's rings. Its surface gleams with an otherworldly luminescence, reflecting nearly all the light that touches it. From a distance, it appears pristine, almost sterile, a sphere of polished bone suspended in the cosmic dark. For more than 3 centuries, telescopes turned toward it and saw nothing remarkable, just another icy satellite among dozens, another frozen fossil of the solar system's violent birth. Scientists catalogued it, measured its orbit, and moved on. There seemed to be no story here, no atmosphere, no geology, no reason to believe anything stirred beneath that flawless white veneer. But in 2005, everything changed. As the Cassini spacecraft arced through the Saturnian system on a routine flyby, its instruments detected something impossible. A plume, not of gas, not of reflected sunlight, but of water vapor and ice crystals erupting from the moon's south pole with the force of a volcanic explosion. The burst rose hundreds of kilometers into the vacuum of space, a fountain of frozen particles backlit by Saturn's pale glow. Mission control fell silent. Engineers checked the data again and again, certain there had been an error. Frozen moons do not breathe. They do not exhale. They do not crack open and release the inner ocean to the stars. Yet there it was. Undeniable, impossible, real. The geysers rose in towering columns, each particle tracing a crystalline arc before falling back or escaping into Saturn's E-ring. Something beneath the ice was generating enormous heat. Something was driving pressurized water through fractures in a crust that should have been locked solid for billions of years. And in that moment, a new question ignited across the scientific community. A question that would reshape the search for life beyond Earth. What force could be powerful enough to keep a world alive in the frozen dark? And if water flows beneath that ice, what else might be flowing with it? The plumes were only the beginning, as Cassini made pass after pass through the icy spray, flying directly through the geysers at speeds that would incinerate most spacecraft. Its instruments began to decode the composition of what Enceladus was exhaling into space, and with each analysis the implications grew more profound. This was not pure water vapor, not simple ice crystals born from some sterile underground reservoir. The samples carried salt, sodium chloride, potassium salts, evidence that the water had been in prolonged contact with a rocky seafloor. They detected ammonia, a compound that lowers the freezing point of water, allowing it to remain liquid in temperatures that should turn it solid. And then came the organics, complex carbon-based molecules, the fundamental building blocks from which life, as Earth knows it, is constructed. But it was the hydrogen that changed everything, molecular hydrogen, H2, pouring from the depths in concentrations that could only mean one thing. Active chemistry was occurring between water and rock, the same reactions that occur at hydrothermal vents on Earth's ocean floor, where superheated water meets volcanic stone and triggers a cascade of energy-rich chemistry. In the crushing darkness of Earth's deepest trenches, these vents stand like chimneys belching mineral-laden water into the cold abyss. No sunlight penetrates here. No photosynthesis occurs. Yet these places teem with life, bacteria that harvest energy not from the sun, but from chemistry itself. Tube worms, crabs, and microbial colonies thriving in conditions once thought incompatible with biology. And now, nearly 1 billion miles from Earth, Enceladus was revealing the same chemical fingerprints. Scientists turned their attention inward, using subtle variations in Cassini's trajectory to map the gravitational field of the Moon. The data painted an astonishing picture. Beneath the frozen surface, beneath 40 kilometers of ice thick enough to entomb mountains, there existed a liquid ocean, not a small pocket, not isolated lakes scattered through the crust. A global ocean stretching around the entire Moon, hidden from view, dark and deep and impossibly persistent. But the discovery raised a question more haunting than any answer. How? Saturn lies nearly 10 times farther from the Sun than Earth. At that distance, sunlight arrives as little more than a whisper, too faint to melt ice, too weak to sustain warmth. By every conventional calculation, Enceladus should be frozen solid, a lifeless glacier drifting through the void. Yet something was generating heat. Something was keeping that ocean liquid. The answer lay not in the Moon itself, but in its orbit around Saturn. Enceladus does not travel a perfect circle. Its path is slightly elliptical, pulled and perturbed by the gravitational influence of neighboring moons. And with each orbit, Saturn's immense gravity squeezes the Moon, then releases it, then squeezes again. A cosmic kneading that flexes the interior, bending rock and ice in an endless cycle of compression and release. Friction. Tidal friction. The same force that creates Earth's ocean tides amplified to extremes. This relentless flexing generates heat deep within Enceladus, warming the rocky core, melting the ice from below, sustaining an ocean that should not exist. It is an engine driven not by fire, but by gravity itself. And so the pieces assembled into a picture both wondrous and unsettling. A hidden ocean heated from within, chemically active, saturated with the elements life requires. But one question remained, lingering in the minds of every scientist who studied the data. Unspoken but unavoidable, was this ocean merely warm, or was something moving within it? The discovery ignited laboratories across Earth. Within months, scientists began constructing artificial oceans, sealed chambers designed to replicate the conditions believed to exist beneath Enceladus's ice. Alkaline water rich in dissolved salts, temperatures hovering near freezing, and most critically, molecular hydrogen bubbling through the darkness, mimicking the chemistry of hydrothermal vents. Then they introduced life, microbes from Earth's most extreme environments, species harvested from deep sea vents, from subglacial lakes, from caves where no light has shone for millennia. Organisms that had long ago abandoned the sun as their source of energy, turning instead to the raw chemistry of stone and water. And the microbes thrived. They consumed the hydrogen. They metabolized the minerals. They reproduced in conditions nearly identical to what Cassini had detected billowing from Enceladus's south pole. The experiments revealed something profound. Does not require warmth, does not require light, does not even require oxygen. It requires only chemistry in motion, energy flowing from one state to another, and time enough for complexity to emerge. The implications reverberated through astrobiology. If life could exist in these laboratory oceans, then perhaps Enceladus was not merely habitable. Perhaps it was inhabited. Some researchers began to draw parallels between the hidden ocean and Earth's own primordial seas, the lightless waters that covered the planet more than 3 billion years ago, before the first cyanobacteria learned to split water molecules and exhale oxygen into the sky. In those ancient depths, life may have begun not at the surface, but at the bottom, clustered around vents where heat and minerals converged. Enceladus, frozen in time and distance, might preserve a living record of that era, a window into biology's earliest chapter. Others ventured further still. Computer models suggested that the ocean might not be static. Convection currents could be circulating water between the seafloor and the ice ceiling above, driven by temperature differences and the moon's tidal flexing. The rocky core might feature volcanic ridges, underwater mountains, vast mineral fields where water and stone exchange elements across geological timescales. In such an environment, chemistry would not be uniform. It would vary by location, by depth, by temperature, creating ecological niches as diverse as Earth's own ocean zones. And if niches existed, then ecosystems might follow. The theories grew bolder with each new paper, each new simulation. Could microbial mats coat the underside of the ice, feeding on nutrients delivered by upwelling currents? Could larger organisms evolve in the depths, adapted to perpetual darkness, navigating by chemical gradients or bioluminescence? Could the plumes themselves be more than passive venting? Could they carry patterns, rhythms, signatures of biological regulation? Some scientists urged caution. Others embraced the questions with quiet wonder. But speculation alone could not answer what lay beneath that ice. Only direct observation could. Mission proposals began to take shape. Ambitious, audacious designs that would push the boundaries of human engineering. The Enceladus Orbilander, a spacecraft that would orbit the moon for years, tasting the plumes repeatedly, then descend to land directly on one of the tiger stripe fractures where the geysers emerge. Cryobots, autonomous drilling probes equipped with heated tips designed to melt through kilometers of ice, descending slowly, patiently, until they breach the ocean itself and release submersibles into the dark water below. Each mission carried the same singular purpose: to sample the ocean directly, to analyze its chemistry in finer detail than Cassini ever could, to search not just for the ingredients of life, but for life's presence, proteins, lipids, DNA, RNA, or perhaps molecular structures entirely unknown to Earth's biology. Yet with each proposal came a sobering realization, an ethical weight that grew heavier the closer humanity came to reaching that ocean. What responsibility does a species bear when it stands on the threshold of discovering life beyond its own world? If a probe descends through the ice and finds microbes drifting in the darkness, organisms that have existed in isolation for billions of years, what right does humanity have to disturb them, to contaminate them with terrestrial biology, to alter, even slightly, the pristine chemistry of an alien ocean? And perhaps more unsettling still, what if the discovery is not microbial? What if the ocean holds something more complex, more organized, more aware than anyone dared imagine? The question hung in the air like the plumes themselves, visible, undeniable, and impossible to ignore. There is a truth embedded in the ice of Enceladus, a truth that extends far beyond the chemistry of its plumes, beyond the heat of its core, beyond even the question of whether microbes drift through its hidden depths. If life exists beneath that frozen shell, it fundamentally rewrites humanity's place in the cosmos. It means that life is not a miracle confined to a single pale blue world orbiting an unremarkable star. It means that life is not fragile, not rare, not a lightning strike of chance that occurred once in 13 billion years and never again. It means that wherever liquid water persists, wherever chemistry flows and energy gradients form, life may emerge, not as an exception, but as an inevitability, a natural consequence of physics playing out across deep time. And if life arose independently in the darkness beneath Enceladus, separated from Earth by 1 billion miles of vacuum, untouched by the sun's light, evolved in complete isolation, then the universe is not the sterile void it once appeared to be. It is seeded with potential. Every icy moon, every subsurface ocean, every world dismissed as dead may harbor its own silent story, written in molecules and metabolisms humanity has yet to encounter. The implications cascade outward like ripples on water. Europa, larger and deeper than Enceladus, locked beneath ice, thicker still. Titan, with its methane seas and organic haze. Ganymede, Callisto, distant Triton, worlds once catalogued as barren, now reconsidered as possible cradles. And beyond the solar system, exoplanets orbiting distant stars, some locked in tidal embrace with their suns, their interiors churning with the same gravitational heat that warms Enceladus. How many oceans exist in the galaxy, hidden from view, insulated against the cold, waiting? The search for life has always been a search outward. Telescopes scanning the skies for Earth-like worlds bathed in stellar light, atmospheres rich with oxygen, surfaces where liquid water pools under open sky. But Enceladus whispers a different message. Life does not require a sunlit paradise. It requires only persistence, only chemistry, only time. And if that is true, then Earth is not the blueprint for biology. It is merely one expression among countless others, a variation on a theme that plays out wherever the conditions align. The forests and oceans, the microbes and mammals, the photosynthetic machinery that paints the planet green. All of it may be one path among many. Beneath Enceladus, life may have taken a different route entirely, adapted to darkness, to cold, to an existence divorced from the rhythms of day and night that have governed terrestrial biology for eons. Yet even if no life stirs beneath that ice, even if the ocean remains sterile, a chemistry experiment perpetually on the edge of biology but never crossing the threshold, Enceladus has already transformed the questions humanity asks. It has redefined habitability. It has proven that warmth can arise from gravity, that oceans can persist in perpetual night, that the ingredients for life can assemble in places far removed from the sun's nurturing glow. It has expanded the boundaries of where life might emerge, and in doing so, expanded the scope of the search itself. Enceladus is no longer just a moon catalogued in textbooks, another satellite orbiting another gas giant. It has become something far more profound, a question suspended in the void, a mirror held up to humanity's assumptions, reflecting back the limits of what was once thought possible. It asks, does life require sunlight or merely persistence? It asks, is consciousness tied to complexity, or could awareness emerge in forms unrecognizable to minds shaped by Earth's gravity and atmosphere? It asks, if life began in darkness, if it thrived without the sun, so then what is life's true nature? What is its minimum requirement? What is its ultimate potential? One day, perhaps within the lifetimes of those who first saw Cassini's images of the plumes, a spacecraft will return to Enceladus. It will descend through the geysers, analyzing their composition with instruments far more sensitive than those carried by its predecessor. It will touch down on the fractured ice of the South Pole, where the tiger stripes carve across the surface like scars. And then, slowly, methodically, it will begin to melt its way downward, kilometer by kilometer. The probe will descend through ice older than human civilization, through layers compressed by their own weight into crystalline opacity. It will pass through pockets where water refreezes, through fractures where currents once flowed, and finally, after months or years of patient descent, it will breach the boundary between solid and liquid. It will enter the ocean. In that moment, cameras will activate in the absolute darkness. Sensors will taste the water, cataloging its salts, its minerals, its organic molecules. Instruments will listen for movement, for currents, for any sign that this ocean is more than chemistry alone, and humanity, watching from a world 1 billion miles away, will not merely be exploring another moon. It will be looking into the memory of its own beginning, into the conditions that may have sparked the first stirrings of life on Earth, preserved here in the cold and dark like a message written in water and stone. Enceladus does not offer answers. Not yet, but it offers something far more valuable, the certainty that the questions are worth asking, and the quiet, persistent hope that somewhere in the darkness, beneath the ice, something may already be listening.